Hi everyone, in this video I'm continuing to work through question 14 part A of the 2020 Extension 2 trial exam from James Ruse. So it's a 3-part complex number question, and I've already worked through part 1 and part 2 in separate videos, so definitely have a look at those if you haven't already. This part 3 wants us to show that 1 on Z2 minus Z1 minus 1 on Z1 minus Z3 minus 1 on Z2 minus Z3 is equal to 0. And I would say this is a pretty difficult question, even at the best of times. But I think what makes this question particularly difficult, and what is most likely the reason why a student sent it through to me and struggled with it, is because I think there's actually an error in the question. I think it is not possible to show this result, and so naturally most students probably wouldn't be able to work out a way to show it because it's literally not possible. So what I'll do is in this video I'll work through the techniques that you would use to show a result like this, assuming that there wasn't an error. I'll apply those techniques to this question as stated, and we'll see that we don't get something that can be 0. And then what I'll do is I'll take a guess as to what I think the question was meant to be, what the question writer probably was intending the question to be, and then show how we can get that to 0. So yeah, let's take a look. So here's what we're being asked to show, and I haven't made any corrections yet, so this is as it's written on the exam. And I think the natural starting point for a question, for this particular question, is to make use of what we just showed in part 2, which makes sense. The questions are kind of building upon each other, because in part 2 we showed that this triangle formed by the 3 points is equilateral, and we did it by showing that all the interior angles were equal. But once we've showed that, we can then rely on the fact that also all the length of all the sides will also be equal. And notice that these sides are formed from effectively the vectors between the points. So the vector formed between point Z1 and Z3, that's got a magnitude. The vector between Z1 and Z2, and the vector between Z2 and Z3, all of these vectors have a magnitude, and we can know that they'll all be the same. So if we come back to our question, we've got the points between Z1 and Z2, the points between Z1 and Z3, and the points between Z2 and Z3. So we're dealing with all 3 of those lines. The order of them isn't particularly important because we're going to make note of their magnitude. So the magnitude is what it is regardless of their direction. So we can say that from part 2, the magnitude of Z2 minus Z1 will be equal to the magnitude of Z1 minus Z3, which will be equal to the magnitude of Z2 minus Z3. And just for the purpose of doing algebra, it's helpful to set this equal to some value, which I'll just call k. And from here, it kind of, I guess, makes sense to start focusing on the first of these magnitudes and see if, when setting it to k, there's certain manipulations we can do that then let us see what we can say about 1 over Z2 minus Z1. So if we start by saying, let's look at the magnitude of Z2 minus Z1 equal to k. A good first step would be to square both sides. So if I just take both sides squared, the reason that's helpful is because now we've effectively got some complex number, its magnitude squared. And one of the first results you'll learn when you're doing complex numbers is that that can be written as the complex number, in our case Z2 minus Z1, multiplied by its conjugate. So Z2 minus Z1, the conjugate. So that can be written as equal to k squared, and that's using that early result you would have learned that the magnitude of some complex number squared is that complex number multiplied by its conjugate. Now from there we can write that as Z2 minus Z1 times the conjugate of Z2 minus the conjugate of Z1, and that leap I've made in taking the conjugate of the difference and writing that as the difference of the conjugates if that's not a result you're familiar with, it's fairly easy to prove. I don't think in the context of this question, a marker would require you to prove it. I think you can take it as a result. But if you've never seen it before and you needed convincing, a fairly simple way to prove it would be just to define Z1 and Z2 in the form A plus IB and actually do the manipulation. So take the difference between those two complex numbers and work out the conjugate. And then take the conjugate of each of the two complex numbers and work out the difference, and you'll notice you get to the same place. So if you need convincing, feel free to go and work through that proof yourself. But for a question like this, I don't think you'd be expected to prove it. So we can now carry on and notice that we've now got something with just Z2 and Z1 in it, the difference. But we want the reciprocal. So it makes sense now to take the reciprocal of both sides. So we could say that 1 over Z2 minus Z1, Z bar 2 minus Z bar 1, that's all going to be equal to 1 over K squared. And now we want to isolate the Z2 minus Z1, so we can multiply this up. So we'll be able to therefore say that 1 on Z2 minus Z1 is equal to Z bar 2 minus Z bar 1 on K squared. And so now we've got our first item of the left-hand side in some format that hopefully is useful. Now, in theory, we could work through these steps for each of the other denominators and then get to the same result because each of them are equal to K, so you can have this same starting point and work through. Now, in an exam, I don't think you'd have to do that. I don't think you need to, in any context, repeat all this. You could just say something like, therefore, similarly, and then draw the same conclusion. Because all we're effectively doing is wherever we had Z2 and Z1, we're just going to have Z1 and Z3, but the working's identical. So we can therefore conclude that 1 on Z1 minus Z3 would be equal to Z bar 1 minus Z bar 3 on K squared. And we can also conclude that 1 on Z2 minus Z3 would be equal to Z bar 2 minus Z bar 3 on K squared. And now that we've got our three ingredients in a new format, we can substitute them into this left-hand side and see if it simplifies to 0. Now, naturally, it's probably not going to, given I've stated that I think there's an error in here in this question, but let's just do it anyway and see what we get. So we can say, therefore, 1 on Z2 minus Z1 minus 1 on Z1 minus Z3 minus 1 on Z2 minus Z3. And now we'll just insert. So it'll be Z bar 2 minus Z bar 1 on K squared minus Z bar 1 minus Z bar 3 on K squared. That's this one here. And then minus this one, Z bar 2 minus Z bar 3 on K squared. So all items are divided by K squared, so we can bring that out, 1 on K squared. And then just repeat all this, being really careful with our negatives. So it'll be Z bar 2 minus Z bar 1 minus Z bar 1 minus minus, so plus Z bar 3 minus Z bar 2 minus minus plus Z bar 3. And now, again, if there wasn't an error here in the question, what would typically happen is all of these would cancel. They'd all cancel each other out and you'd get 0 and you'd be done with the question. But in our case, the only things that cancel are the Z bar 2s. The Z bar 1s have the same sign and the Z bar 3s have the same sign. So actually this is 1 on K squared times, we got 2 Z bar 3s minus 2 Z bar 1s. And again, if you want to, you could factor out this 2. It's not going to help us at all, because we'll get 2 on K squared, and we're still stuck with this Z bar 3 minus Z bar 1. And actually, the only way this gets to 0 is if z bar 3 is equal to z bar 1, so that, 1 minus the other gets you nothing. But we know that can't be the case. In the context of our question, z bar 3 and z bar 1 can't be the same. If we go back to our triangle, we've got an equilateral triangle. If z bar 1 and, for z bar 1 and z bar 3 to be the same, then z1 and z3 would have to be the same, so the conjugates become the same. And for that to be true, we wouldn't have a triangle anymore, because these two would just form one point, and effectively we just have a straight line. But we know we're dealing with an equilateral triangle. The fact that we've got an equilateral triangle is what allowed us to have this starting point in the first place. So these two can't be the same. So we can with quite a bit of confidence say this is not equal to 0. And I would argue, if I'm the question writer writing this question and I've made this oversight, this mistake, if I saw this on the exam, I'd be giving full marks, no question, because this is even better than doing a proof like this. It's going above and beyond really to prove that actually there's an issue with the question. I couldn't imagine many students would, but it is James Ruse after all, and if you're familiar with schooling in New South Wales in Australia, James Ruse is very well known as one of the top performing schools, actually the top performing school for many, many, many years. So, maybe it is the case that there's some students who, when taking this test, were able to, spot the error almost. But, at the same time, you can imagine there's many students who would have just wasted their time and energy in the exam trying to prove something that isn't actually true. So I think it's unfortunate. I would hazard a guess that the teacher has noticed the issue and fixed it up, and I'm not sure what they would have done. Maybe they would have just either not marked the question at all or given everybody the full marks. Who knows? Probably could have been potentially awkward and controversial. But there definitely is floating around out there a version of this trial exam where the issue hasn't been fixed, and so there's students out there trying to grapple with something that actually can't be shown to be true. So hopefully that's made sense in terms of what working I have done and the techniques I have used and why it can't be 0 like we're being asked. So what I'll do now is I'll turn over and I'm going to restate the question as what I think it was meant to be. And the hint is, how I worked this out was knowing that at this point everything's meant to cancel. Well, all you really need is a simple signage change and you're going to get there. So I'll just turn over. And what I think the question was meant to say is that we should have been asked to show, and it's really just one change. It's if I just highlight it in a different color, I think it's this item here. Instead of Z1 minus Z3, it should have been Z3 minus Z1. So let's do that. Let's say we want 1 on Z2 minus Z1, Z2 minus Z1, minus 1 on Z3 minus Z1, minus 1 on Z2 minus Z3. I think if the question said show that is equal to 0, we will get there. And again, rather than repeat all of the working, we can start, well, we can use essentially the same approach, take each of these denominators, know that their magnitudes must be equal and set them to k, and you're going to get this result. So we can write this result 3 times just using the correct denominators. So we can say, using the working, if we were doing this for the first time, we'd work through it properly, but we can say 1 on Z2 minus Z1, this first item here, 1 on Z2 minus Z1 is equal to Z bar 2 minus Z bar 1 on K squared, Z bar 2 minus Z bar 1 on K squared. That is exactly what we worked out anyway. And then you'd say similarly, and you'd write out the other two. So we have 1 on Z3 minus Z1, would be equal to z bar 3 minus z bar 1 on k squared, and 1 on z2 minus z3 would be z bar 2 minus z bar 3 on k squared. So now let's insert these into our left-hand side and see if it all cancels. So we'll say, therefore, 1 on z2 minus z1 minus 1 on z3 minus z1 minus 1 on z2 minus z3. That's going to be z bar 2 minus z bar 1 on k squared minus z bar 3 minus z bar 1 on k squared minus z bar 2 minus z bar 3 on k squared. And let's be very careful with our negatives. We'll bring out our k squared, 1 on k squared, we can do that. And then we'll have z bar 2 minus z bar 1 minus z bar 3 minus, so plus z bar 1 minus z bar 2 minus, so plus z bar 3. And as you would hope, z bar 2 and minus z bar, oops, that should say z bar 2, because that's minus z bar 2. So z bar 2 and minus z bar 2 cancel. Minus z bar 1 and plus z bar 1 cancel. And minus z bar 3 and plus z bar 3 cancel. And so you can, with confidence, conclude that that must be 0, regardless of k, regardless of their magnitude. So that is what I believe the question should have looked like. And that is what the proof would look like, noting that I've just started from this point here. So you'd want to work through this properly if you were doing it from scratch. All right, so there you have it for that part 3. I think a little bit controversial. It's always I'm always a little bit reluctant to claim that a question has an error. I did do a lot of trying of many other things to try and prove that this could be shown to be 0, but I just kept coming back to the fact that everything led to this, and this just simply can't be true in the context of our question. So yeah, if you were struggling with this part 3, I wouldn't be too discouraged, because you know it's always going to be hard to answer a question with an error in it. So take heart that you know, it probably wasn't entirely you not being able to work it out. But setting all that to the side, you know, hopefully this technique has made sense to you, and it's a technique that you can add to your toolkit, because you know, it's a handy one to prove something like this. I think it all came down to noting the equilateral triangle meant the magnitudes were the same. That's step 1. But then doing our manipulations to get this reciprocal, and it all came down to this result here, and just being able to see that. So yeah, hopefully you found all that helpful and that's all made sense. And yeah, tick boom.